Hey gang, sorry for the interruption. But again, where I left off was here in number 2, where it talked about when you have a isometry or reflection of a plane figure. Again, that means you either have reflectional symmetry or sometimes it's called line symmetry. Alright, so moving on to the next page here. Here it kind of reminds us of what reflectional symmetry is. So the red dashed line, that is your line of reflection, and then it's highlighting the blue side here, then the blue side on the other side. So again, that line of symmetry cuts it in half essentially. And then it asks how many lines of symmetry for the pentagon. Remember, any regular polygon is going to have the same number of lines of symmetry as it does sides. So this one's going to have 5 lines of symmetry because it is a regular pentagon. So down here, it wants us to draw all lines of symmetry following the regular hexagon. So we did this before. So again, if I just draw in the lines of symmetry here, remember you're going to have one for each side. So there's 1, 2, 3, and then the angles can also be bisected in half. 4, 5, and 6. Now over here, again, I'm going to have one line of symmetry down the middle. Whoops, that was terrible. So again, I'm going to have one line of symmetry down like this. Then another line of symmetry like this. So it only has 2. Notice that I can't use this as a line of symmetry. Just want to point this out. This diagonal can't be used as a line of symmetry because when you fold this over, it has to map onto itself. So when I fold it over, if you kind of keep your eye on this corner and I try to fold it over to this one, that corner is going to end up over here, and that's not mapping onto itself. So that red line is not a line of symmetry. Down here, it says for each figure, find all the lines of symmetry that you can. So an isosceles trapezoid, I only see one line of symmetry right here. Scalene triangle, I got nothing for you. I don't see a line of symmetry anywhere on that. An ellipse, that's this shape right here. Again, it's going to have 2 lines of symmetry, kind of like the rectangle did. Got like one through the middle like that, and then one like this. Rectangle I just showed you up above. Line of symmetry, line of symmetry. Parallelogram, the only way a parallelogram could be have reflexive symmetry is if it was a rhombus, but this one doesn't look to be a rhombus. So again, if I try to use this as a line of symmetry here, when I try to map this over to the other side, it's going to end up over here, not on the figure at all. So that parallelogram does not have any reflectional symmetry. Even if I tried to like cut it down the middle, something like this. If I try to use this as a line of symmetry, again, this part up here, when I fold it over here, is going to end up off the figure. So there is no line of symmetry for that parallelogram because of that reason. The isosceles trapezoid got no reflectional symmetry. A circle, on the other hand, that's a little more complex. So again, I got one line of symmetry here, another one here. The isosceles triangle, that's easy. We showed you that one before. There's your line of symmetry. So those are different shapes in their lines of symmetry. This number 6 talks about rotational symmetry. Again, rotational symmetry, I have to have a center of rotation. So over on this one, my center of rotation is going to be right there. Then I see I have 1, 2, 3 equal parts. So again, if I rotate this, this part over here, if I go clockwise, would end up right on there. And again, since it has 3 equal parts, I can figure out the rotational symmetry by taking 360 and dividing by the number of equal parts, which in this case is 3. So I would say this has 120 degrees of rotational symmetry. Then on this shape here, I notice I have a Z. Here my center of rotation is going to be right here. So if I count that as my center of rotation, I see these equal parts basically right here and right here. So that means there's 2 equal parts. So that would mean if I spin this clockwise, this intersection here is going to end up there in 180 degrees. So there's 2 equal parts here, so it's a 360 divided by 2. So I would say this has 180 degrees of rotational symmetry. On the swirly thing, I noticed that I have a center right about here. So So my center of rotation is basically right there. And again, I count these 3 equal parts. Again, I take 360, divide it by 3, and that gives me 120 degrees of rotational symmetry. Over here on this shape, again, my center would be here, and then I count 1, 2, 3, 4 equal parts. So for this one, the rotational symmetry would be 360 divided by 4, which is equal to 90. 4 equal parts. So it's got 90 degrees of rotational symmetry. So down here, it says, do the regular polygons have rotational symmetry? Again, the triangle, we figured that one out. Again, that's going to have 120 degrees of rotational symmetry because it got 3 equal parts. Over here, again, it's going to have rotational symmetry of this much, which is 360 divided by 4. So that, I'm sorry, yeah, 360 divided by 4. So that'll be at 90 degrees of rotational symmetry. This is the one I showed you on the opening video. Again, if my center is here, again, if I focus on this side here, it's going to rotate clockwise till it comes to here and it maps onto itself again. So again, it rotated this far, of which there's going to be 5 of those central angles. So this would be 360 divided by 5. And if you divide 360 by 5, I forget what that was. One something. 360 divided by 5. So that's 72. 72 degrees of rotational symmetry. Hexagon, again, we went over that before. Again, it's going to rotate one of these central angles till it maps onto itself. So that's 360 divided by 6. So 360 divided by 6 is 60. So this has 60 degrees of rotational symmetry. So then it says generalize. What would be the degree of rotational symmetry of an n-gon? Well, this was 360 divided by 3. This was 360 divided by 4, by 5, by 6. So if it's an n-gon and it has n side, you can figure out the rotational symmetry by just taking 360 and then dividing it by n. So that'll give you the rotational symmetry for any regular polygon. So down here, I said we come back to a circle, and here's an example down here of a circle. How many lines of symmetry does a regular n-gon have? Well, it's going to have the same number of sides, so it has n lines of reflection. And it says, how many lines of symmetry does a circle have? Well, I showed you a couple before, but it turns out I got an infinite amount of lines of symmetry. So this is infinite. And then it asks, what is the smallest degree of rotational symmetry? Well, basically, I can spin it really, really small, really, really big, and it's always going to map onto itself. So because of that, that's called an infinitely small angle of rotation. So it has an infinitely small degree of rotational symmetry, basically, until it ends up and maps onto itself. So then it has this chart that we need to fill in here, and it talks about different symmetries, line reflection, if so, how many, rotational symmetry, and what's the angle. So over here on this shape, again, looks like to be an isosceles trapezoid. I would say yes, it has line symmetry. How many lines of symmetry it has? I only see the one line going down through the middle. Does this have rotational symmetry? No, I don't think so. Since it doesn't have rotational symmetry, we don't have to worry about the angle. Down here, it looks like I have a square, so I'd have a center of rotation there. Oh, I do have lines too. Remember, there's one for each side. So I'd say yes. It's got 4 lines of symmetry. Does it have rotational? Yes, we talked about that. It's going to be 360 divided by 4. So I would say this has 90 degrees rotational symmetry. The letter J down here does not have any line symmetry at all, or reflectional symmetry. There are no lines then. Does not have any rotational symmetry either. So I don't have to worry about getting an angle on that one. Star, I looked at that in the opening video there. So this does have line symmetry. So let's see if we can find them. Here's 1, 2, 3, 4, 5. So I see 5 lines of symmetry there. Rotational symmetry, it definitely does. And again, I got 1, 2, 3, 4, 5 equal parts, so I would do 360 divided by 5, which was what, 72 degrees? So I'd say this has 72 degrees rotational symmetry. This arrow looks like I have 1 line of symmetry right down the middle. I don't have any rotational symmetry on that one. This tile down here, definitely see some line symmetry. How many lines do I have? So let's see, I got 1, 2. So this would also be symmetric, and so would this. So that one's got 4 lines of symmetry. Rotational symmetry definitely has that. So rotational symmetry.
Slightly better, but still
good.
Not successful.
Good. Rotational symmetry. Again, there's my center of rotation. Again, I have 4 equal parts on this, so I would say yes, it has rotational symmetry. It's got 90 degrees, 360 divided by 4 on that one. This one's wagon wheel here. I definitely have some line symmetry. So basically I have what? 1 here, 1 here. So if I go right down the middle of the spoke, 3, 4. But then I also have line symmetry if I go down this way. So that's another one. So how many total is that? 4 through the spoke, and then 4 through there. So that's a total of 8. Got 8 lines of symmetry there. Definitely has rotational symmetry on that one. Let's take a look at it a little bit clearer. So I got to look for equal parts here. So it's a yes. Equal part would probably be one of these little triangle things right there. So there's 1, 2, 3, 4, 5, 6, 7, 8 of those. So this would be 360 divided by 8 to get that rotational symmetry. And then 360 divided by 8 is 45. So the rotational symmetry on that would be 45 degrees till it maps onto itself. This one down here, this one, if it has lines of symmetry or not, jeez. I guess if those X's were drawn right, I could draw a line like that. That would have a line of symmetry. Or no, wouldn't. It would not. Because when I fold it over, this would not, it would map over right there. So I don't think this has a line of symmetry. Let's try the other way. The other way that you would have a line of symmetry is this way right here. Try to think if I take that and map it over here. I don't think it would end up, so I don't think there's any lines of symmetry here. Rotational symmetry. This might have rotational symmetry. So kind of if I split it up like this and I rotate it over this way 180 degrees, then I would say it's got 2 equal parts. 360 divided by 2 is 180 degrees. Book, the way it's written here, I see 1 line of symmetry like this. And I don't see any rotational symmetry. Looks like I'm running out of time here. So this one, it looks like I have 2 equal parts. If I call this the center, oh, line rotation, none. It does have rotational, and it looks like it's at 180 degrees because I see 2 equal parts. If I use that as my center of rotation, so that's 180. This one, I got a couple lines of symmetry. No, I guess I just have 1. If I use the sand in there, I would say I just have 1 line of symmetry. Rotational wise, I wouldn't say there's any. On this hat, I see 1 line of reflection. but I do not see any rotational. So that is line symmetry and rotational symmetry.